So hello everybody, I'm pleased to be there. It's my first time in Bombay, or first time in India, so it was, so I missed the beginning of the talk of Sudeshna, but he speak a lot about CMS, and as Govinda said, I was in CMS before CMS, in fact, because I was first a technical student at CERN in 90, and it was the beginning of the idea that perhaps we could make a electromagnetic calorimeter of crystals in LHC. There was no, so for 6 months I tested a very small sample like this. I remember 1 cubic centimeter of barium fluoride. And at this time, I met some people from Bombay, Dr. Raghavan. And then I came back for my PhD in September 92. And as you say, the topic of my thesis was looking for the best scintillator for a possible electromagnetic calorimeter at LHC. And in fact, we just celebrated the 30 years of CMS in December 2022. So the LOI, the letter of attendance of CMS, was written in 92. And then in 94, CMS decided to use crystal calorimeter on PVO. So this is a long story, but so you never know what's happened in your life. And it's true that I spend all my time in CMS, but many applications. So I have 2 times, I have 1 hour today and 1 hour tomorrow. So probably today I will be more on the generality, and tomorrow on application, or also on the recent development on scintillator. So just to remind you, what is the scintillation principle? So when an energy of incident particle is converted in light by the material, so you have high energy particles, so gamma, electron, positron, and the energy is absorbed by the crystal, and crystal will produce light. And in fact, the energy, the number of photons is produced is proportional to the energy of incident particle. And of course, with only a crystal, you cannot do something. You need something to measure this light. And we use what we call a photodetector. So this is, for example, the photodetector was used in CMS experiment, avalanche photodiode. And this photodetector will convert the light in electrical signal, will be read out after by electronic, and Christophe will say all the things on the electronic. And the number of photoelectrons that you collect in the photodetector is proportional to the number of photons, so proportional to the energy. So there is different type of scintillator. So we classify into organic scintillator. So generally, you can find, so organic scintillator exists in 3 types: crystal, liquid, plastic, low density, low atomic number, relatively quite good light yield, decay time quite fast, and one of the problems is that they are not so radiation hard, but you can find in different shape. And then you have inorganic scintillator. So you have liquid noble gas, but this work only at cryogenic temperature. And I will speak much more on this because it's on what I work. It's a crystal who are generally, who can have high density, so it can go up to 9 grams per cubic centimeter, IZ. Light yield can vary from very low light yield like PVO, but up to more than 70,000 photons per MeV, and decay time varying depending on the crystal, and quite good radiation hardness. So I will, as I say, I will speak more on inorganic scintillator. I don't know what to do. Okay. So I will come back that later, but in fact, the selection of the scintillator will depend on what you want to do and the requirement of your application. So I think in the previous talk, you were mentioning plastic or crystal, depending if you have an absorber in front or not. So we classify, it depends on the density that you need. The light, so if you need to have a high stopping power, you will look for crystal with high density. If you want to have a very good energy resolution, depending on the energy you are working, you will need a high light till. Decay time is if you want to have fast timing, you need fast timing. Radiation hardness, so it depends on the application. And in high luminosity LHE, we need radiation hard materials. But what is also very important is that you can have very good scintillator, but only that exists in a small pieces. So if you want to build a large detector, you need to be sure that you can manufacture and have in a large quantity. And of course, that if you have a large quantity, that all the material are the quality is homogeneous. So this is the reproducibility. And of course, when you build a detector, a large quantity, you want that it's easy to do, and also that the cost is realistic. So all these are important for the choice of your scintillator. And many applications are using scintillator: astronomy, high energy physics, medical imaging, X-ray and gamma spectroscopy, monitoring in nuclear plant, neutron, oil well drilling. I will mention some of these applications, but I will focus more on high energy physics and medical imaging, and particularly on the PET. So now a few words on organic scintillator. So the scintillation in the organic scintillator are due to transition between energy level at the level of a single molecule. And usually it's for example, in the P molecular orbital in benzene. So the fact that it's at the level of a molecule, you can find this organic scintillation. So you have, you have a very fast emission that is fluorescent. So it's the emission between a singlet level, but you can have also a transfer to triplet level who are slower. So you have phosphorescence. And in fact, the fact that it's at the level of a molecule that you can observe independently of the physical state. So it's why you can have either a scintillation also in pure organic crystals and liquid or plastic scintillator. So organic crystal, here are some examples that you can find. It's, for example, on Transcend and Steelbend, you can grow crystal of these materials. And depending on the material, the emission wavelengths will be different. So you see here it's a different example, and it's vary from 350 to 500 nanometer. And you can have quite relative high light yield. So in case of anthracene, you can go to 20 photons per milliliter. But of course, what is more used and known, it's a liquid and plastic scintillator. So the principle is that you have generally a base or a host material, and then inside you put some fluor or dye, and you put one or two dye. So what will happen? You have first ionization in your in the molecule on your polymer, and then this will desexcite to transfer the energy to the primary fluor, who generally, depending on what, but generally you have emission in UV, 340 nanometer. It's why you use a second fluor to shift the wavelengths of emission toward more visible light. And so you add, and then you read out with a photodetector. And this, we call that wavelength shifting. And so here are what's happened. So you have emission of your base, then transfer of energy to the primary fluor. And the idea is that the second fluor has the excitation band corresponding to the emission of the first fluor. So all the emission of the first fluor is absorbed by the second one and re-emitted after at a longer wavelength. And here are typical the material that you use for polymer, so for base. So, and these are the fluor, and so And if you look on I took an example of two web page, but there is a lot of liquid scintillator. And so here again, it's depend on what you want to study, but generally they are very fast. And the same for the plastic scintillator. So you can look on these two web pages, and depending on what you want to do, you can select your materials. And the advantage of a plastic scintillator, for example, is that you can really do the shape that you want. So you can see here some example. So you can use also in form of bulk, but also you can do fiber. And also you can have a very large volume of plastic scintillator. So here it's an example where you have a long plastic scintillator, and then you have light guide to collect the light to the photo detector with here. And the principle for a wavelength shifter, and I think it was also mentioned in previous talk. So here is two examples. So here you have a tile of plastic scintillator. Inside you have some fiber, and then the light produced by the tile is transported by this fiber outside to the photo detector. And this is another example where you have what we call Shashlik module, where you have absorber and plastic scintillator tile. And then you have a fiber of wavelength shifter who allow to transport the light from each tile to the end of your module. So now concerning the inorganic scintillator. So quickly on liquid noble gas. So this is the fluorescence mechanism in an atomic process. So this is example of argon scintillation. So you have two processes. Either you have excitation, direct excitation of your argon, and who will combine with another molecule to make, and then by this excited molecule will go back to the fundamental level by emitted scintillation light, or you have ionization and again emission of light. So the problem of this is that you need the emission is in VUV, and you require cryogeny because to have liquid materials. And these are, and I think I have one example, is something that is used particularly for experimental on dark matter, where you look for, you need large volume of scintillation. And here are some example of liquid argon, properties of liquid argon and liquid xenon. So now inorganic crystal scintillator. So it's a long story. In fact, the first material was where we find some light was calcium tungsten and zinc sulfate. So in early 19. And then in 14, there was the invention of a photomultiplier tube, which allowed to really make a study of the various scintillators because you could measure the light. And another date that is important is in the 90, because up to 90, people were using material. They know quite a lot, quite well the phenomena of luminescence, but really the science of scintillator, people didn't understand everything on that. And then in 90, when there was the request for LHC, in fact, it was really the build of the born of the scintillator birth of scintillator community. And there was two things that there was the creation of Crystal Clear, who was to find the best material for future calorimeter. And through that, there was the creation of the SIN conference. The first one was in Chamonix in 92. And now we meet every 2 years to discuss scintillation. And starting from that, people start to really going in depth to understand all the scintillation process. So here it's a small animation to explain what's happened. So when high energy particle enter in the crystal, it will interact with the electron of the atom of the crystals. And by recombination, you will have light. And this is a simple model. But what happened here? It's this model was in fact well explained by Andrei Vassiliev. So this is the case of you have emission due to doping with rare F. And here it's all the process of the scintillation. So from the creation of hot electron-hole pair. And then you will have excitation of electron-hole pair until the energy, you have enough energy to create this electron-hole pair, who are proportional to the energy of incident energy. And at a certain time, you have not enough energy to create more electron-hole pairs. So you have, in fact, a thermalization of the electron on the hole from the up to the top bottom of the covalent bonds on top of valence bands. And then this electron on hole will be captured either by defect or by the luminescence center who will desexcite emitted some light. So this is so you have first the creation of a certain number of electron-hole pair, and then you have transfer of energy to the luminescence center, and then the recombination. And this took some time. And with all these steps, you can evaluate the absolute scintillation even that you could have in your scintillator. But of course, it depends on the efficiency of your energy transfer. And and this is show you that indeed it's the light output of several material who has been done by a colleague from Delft some years ago. And you can see that it really follows this is the light output versus the energy gap. And you see that the smaller is your energy gap, higher you can have, higher light yield you can have. The emission and the properties of the scintillation is dependent on the materials. So the emission, so here, for example, you have a picture of 3 crystals. So this is the LYSO, so it's emitted at 420 nanometer. Here you have BGO emitted at 500 nanometer, and this is GHG, who are more than 530. And why it's different is because, in fact, the emission wavelengths depend on the energy of your between the fundamental and excited state of the luminescence center. And so depending on the energy between the two levels, you will have different color of emission. And here you see a few examples of crystals. And in fact, the emission wavelengths can depend also. We speak about intrinsic or extrinsic scintillators. So, for example, BGO, the level who are responsible for emission are intrinsic to the crystals. Some other material like lutetium, aluminium, garnet, or orthosilicate of silicium are extrinsic scintillators. So you need to add a dopant to have a good emission. And for example, just to illustrate, in the case of lutetium, aluminium, garnet, you can dope with praseodymium. And in this case, you will have emission in the UV. While if you dope with a cerium, you will have emission in 520 nanometer. And this is due to the fact that depending on the dopant, the energy level are different. So we characterize also the scintillation by its emission, but also an important parameter is the decay time. So this is a typical pulse shape that you can observe if you put a crystal in a photodetector, we excite with the source. And in fact, you have always a rise time, sometimes it's very low, and a decay time. And then sometimes you can fit up the decay time by one exponential, but generally you have several exponential, and this is the generic formula to describe the pulse shape, the decay time of your scintillator. And here again, the decay time will change depending on the materials. And here are a list of a certain number of crystals who are quite used. And so you can see that the density can vary from, let's say, 4 to 8 for the LUAP. And often you have a high index of refraction. So this could be also, I will go later on that, but mean that you have a lot of internal refraction. The emission, so you see it can vary from deep UV to 50 nanometer. And the decay time, you can have very fast, like barium fluoride, I will come back that. PVO was one of the main reasons why we select that. And slow like NI. And volatile is also different. So you see that in case of, I think there is a no. Yeah. In case of PVO, it's 200 photons. So it's not a lot compared to the other, but we use in high energy physics. So 200 photons per MeV, it's a lot of photon when you are at the level of GeV. And so we classify, as I said, mainly by this 4 parameter. And if you group, in fact, the list that I showed you before in this plot, you see that unfortunately, you don't have a crystal who have high light yield, short decay time, high energy resolution, and high okay. So we are looking for that, but unfortunately, you cannot have all. So you have always to make some compromise or find some new idea to combine the different properties. So I thought it was also important. Perhaps you are doing some practical exercise during the afternoon on Scintillator, but just to tell you that which parameter when we characterize crystal, it's important to know. So transmission, radiation damage, light yield, energy resolution, and decay time. And all that you can measure in the lab, in fact. Well, radiation damage, you need to have access to a radiation source, high radiation source, but the rest, it's something that is quite classical in any lab who are dealing with a scintillator. So the transmission, so what we do is you inject a light. So usually you have a monochromator, so you scan different wavelengths, and you have a beam, you enter the crystals, and then you compare the intensity of the light entering the crystal and the light exiting the crystal. So you measure longitudinally and also transversal. And with the transmission, you can learn quite a lot of information. So one important thing is that I told you that you produce light in your crystal, but then the light, you collect generally the light at one of the exits of the crystal. So the light will travel inside the crystals. So you have to be sure that the wavelength of emission is not absorbed by your crystal. Otherwise, you will lose a lot of light inside your crystals. And for when you want to measure very precise energy resolution, this could be a problem. So it's really important to be sure that your crystal is transparent in the emission. So here you have emission spectra, here you have a transmission. So it's important to check that you have a quite good transmission in this region. So here it's an example of what some crystal. So this was a PVO crystal was really yellow. And you see that we had a strong absorption burn at 420 nanometer. And by doing some improvement on raw material and a growing process, we have been able to improve the transmission. You see here it's a theoretical transmission, so only due to loss of, due to Fresnel loss, so optical, you know, at each time you have a reflection into surface, you have some intrinsic loss. And you see that the crystal was transparent. And that was really important because the emission of PVO is at 420 nanometer. And it's also, if you measure also transversally, it gives you also the uniformity of your the transmission. So I think so this show also some plot, but radiation harness, why is important? So I remind you, you have the emission and the transmission. So if by damaging you have loss of transmission, the light that is produced will be absorbed. And this, again, you will measure less light with. So for the same energy deposit, if your transmission with time decrease, you will measure less light for the same energy. So you will have an error, or you will sous-estimate your energy. So, and in fact, here you have a correlation, and you have a really nice correlation. So this was an exercise that we did. So we calculate, we classify, we compare the transmission before and after irradiation, and we characterize by what we call induced absorption, with the ratio of initial and the transmission before and after irradiation. And then you measure the light, and you see that, in fact, with the light, if you have a damage, increase of your induced absorption, you will have a loss of light hill. It's why experimentally in CMS, we follow the transmission of the crystal during the operation to be able to correct, because once you know that, you can correct the transmission, the loss that you have due to the transmission degradation. So it's what we call a monitoring system. Another parameter is the light output. So how you do that? So you have a small radioactive source. So usually in the lab, we use sodium 22 or cesium 137. And then you have your crystal and your photodetector. So you put the source at the top. And then you measure what we call photoelectric spectra. So either all the energy will be absorbed by the photoelectric effect, and you will have this peak. Some of the gamma will be scattered, and so you will have only a partial energy. So it's what we call Compton, and you see the Compton edge. And some will be back scattered, so you will have also lower energy. So by measuring the spectra, you can deduce the light hill. So the light hill is given by the position of your maximum of your photopeak, normalized to you calibrate your system by the single photoelectron. And also what is important is the energy resolution that is defined as the full width of mass, half of max of your photopeak. And so normally, if your crystal will be perfect and without defect, your photopeak, your energy resolution could be only due to the photostatistic. So here again, example of different spectra depending on the crystals. So as I have seen in the table, you can have really high light hill or low light hill. And so the energy resolution, so there is a part which is due to the photostatistic, but also part which is intrinsic to the crystals. And this value can vary from one crystal to another one. So here it's the energy resolution what was measured on two different crystals in the lab. And here was the energy resolution that if you consider only the photostatistic, and you see that you have a difference. And in fact, this is, well, there was a lot of understanding on that. And one of the reasons is that normally we consider that we hope, and as it was said, at high energy, that you have your light hill is energy. So whatever the energy is absorbed, you have the same light hill when you normalize to photon unit of energy deposit. So what you see here, for example, is the same crystals, but excited with different source. And then if you plot the position of the photopeak in function of your energy, you see that you are quite linear. But in some case, and here is the example for LUAP and LSO, if you measure the light output of the same crystal with different energy, particularly at low energy, and here it's normalized to the light hill at cesium 137, you see that in case of LSO, if you excite with 100 keV, you have 50% less, but if you excite with the cesium 137. So it's what we call the non-proportionality, and it's characterized by this value. And in fact, it has been, so some colleagues measure for different materials. And in fact, if now you plot you look energy resolution in function of the yield, you see that the red, it's only the photostatistic. And then you see that some crystals like YAP are very good, and in fact, they have a very small non-proportionality, while in case of LSO, sodium iodide or cesium iodide, you have a big difference of energy resolution compared to the pure photostatistic term. And you see that these crystals are the ones who are the less proportional. So there is a direct correlation. And now we think we understand that there is some interaction between inside the material to make this non-proportionality. But here, if you look the YAP, for example, this was two different YAP, and also the quality of the material is important. So defect or impurity. So, and another characteristic that we are using, and more because we want to, for timing, it's what we call time coincidence resolution. So for that, what you do is you use two identical crystals, or you have one reference, you have a sodium-22 source, we emitted 2 gamma in opposite direction, and then you measure the difference of the time of arrival of the two systems. And like this, you determine the delay histogram. So you select the photopeak on both sides. So like this, you are sure that it's a coincidence event. And making the delay histogram, the full width of maximal will give you the time resolution. So I thought also it was nice to show you how we grow such material. So there is different technology. So one is called vertical Bridgman technique. And due to the name of people who put that. So in this case, you have an ampoule with close, and you put the chemical product of the crystal you want to grow. You melt, and then you put this is in an oven, and you have a gradient of temperature. And when it's colder, there is crystallization who is occurring. But this is closed. So in fact, the shape of your crystal is depending on the shape of your ampoule. Another technique is a Czochralski technique from Mr. Czochralski. So in this case, you have an open crucible. So here again, you have a melt. So you put the raw material here. And at the top of your liquid, you have either a small crystal of what you want to grow, so what we call seed, or some iridium wire. And at this interface, here again, you have a gradient of temperature, you have a crystallization which is occurring, and then you pull up, and progressively the crystal will grow up. So depending on the melting temperature of the material, you will use different types of crucible because you want to be sure that your crucible doesn't melt and you lose. So it's why, for example, LYSO, they use the iridium because they have the melting temperature is above 2000 degrees. So. And this is so here you have a very nice picture to really show you what's happened here. So this was a PVO crystal. So here you see the crucible, the heating system. And here you see the seed. And this is at the end of the crystal. So you have what we call an ingot. And then you have to cut and polish to get the shape that you want. And this is another example of YAG. Produced by Kritur. So here I forget to put the dimension, but here typically I think it was 6 centimeters, while in the YAG now they are able to grow crystal with 14 centimeter diameter and 14 centimeter long crystal. So, and of course this has you need to adjust because it's quite heavy. So, and also you have to adjust the size of your crucible. So, and another technique that is more recent is that I told you when I present plastic scintillator that you can do any shape that you want. And now it's also starting to be possible with crystals. So this is the technique of a micropoulinden technology. So it's similar to the Chokralski, but at the bottom of your crucible, you have a die. And then you put a seed just at the interface. So you see in this picture, you have the crystals, you have a drop, and you pull down. And then you can grow crystal fiber. And so here you see some picture of crystal fiber of 2 millimeter diameter. So the advantage is that you can have a wide range of diameter. So from 300 micron to 3 millimeter. Above 3 millimeter, it's not really, and it's better to do the fiber directly from the ingot. But you can play also the geometry of your fiber depend on the geometry of your hole at the bottom of your crucible. So you can have a square or even hexagonal. So it's faster than to grow a big crystals. And also you can have a crucible with different holes. So like this, you can pull down several fiber like doing spaghetti. And so this is opens some new possibility. Another technique is used for sapphire. In fact, it's a bit like a micropoulinden system, but here you grow a plate. So you see you can grow several plates of crystals. And here are some examples of tests who were done on lithium aluminum garnet by a colleague in Japan. And now, you know, we speak a lot of 3D printing. And this technology is also going up for materials. So here it's an example of a colleague who developed that in Kurchatov Institute. So you see, but it also exists now also for plastic scintillator. And I think the development of plastic scintillator will go faster than inorganic crystal because, but you see that the shape that they were able to do. And so this, it's also open a way to have some crazy idea of design of future detector. It's not for tomorrow, but perhaps for the day after tomorrow. Okay, so a few words on a photo detector. So the principle of a photo detector, so it's convert the light in electrical pulse. So you have three main steps. So you generation of a primary photoelectron or electron ampere, depending on the type of photodetector. Then you will amplify the signal, and then you will collect the secondary electron to form the electrical signal. So what is important is the quantum efficiency of photo detection efficiency. So for a given wavelength, how much the photon will be converted in photoelectron, the gain, the dark current or dark noise, energy resolution, dynamic range, because you have to be sure that your photo detector is linear, the time dependence, and this is important for timing, and also how we can cope with the rate of your. So there is different type of photo detector. I will not go through all, just give you a so photomultiplier, microchannel plate, hybrid photo detector. I think today's now parle on that. Gaseous photon and a solid state photo detector, where you have silicon photodiode, avalanche photodiode, and silicon photomultiplier with, I'm sure you have heard because it tends to be the photo detector à la mode. And so photomultiplier, I'm sure you have used during the last week already or this week. So this is also different, a table summarizing the characteristic of a photomultiplier. And so you see there is the gain is important depending on the number of photons that your scintillator is emitted. What is also important is some application for photomultiplier, for example, you need usually a quite high voltage, while in SCPM, which are not here, in fact, you need a lower bias voltage. So this is the principle of photomultiplier, but probably you have already a course on that or some. So just so your photon arriving in the window, then you will convert by the photoelectric effect, and then the electron will be multiplied. There will be a multiplication by passing through different D node, and this will give you the gain. And one of the disadvantage of photomultiplier is that it's sensitive to magnetic field. And this can be a problem. So for example, in CMS, we could not use for the PMT for electromagnetic calorimeter. And also you need quite high, to power high voltage. So this, for example, for some medical application could be a problem if you have too much, if you have to put some device close to the patient to have 1000 volt is not very nice. It's better if you have only few volts. So if you look on the web page of Mamatsu, you could see that you have all the size of PMT exists in the world. So this big one, and now I'm not sure they have it, but they even do a photomultiplier who are corresponding to a piece of your really small. And the quantum efficiency is really dependent on your photocathode. And so depending on which crystal you want to study, you will select one or other depending on the photo detection efficiency. So if you want to look for UV light, you will not select this one because you see the quantum efficiency drop at 450, but you will better use this one. If your emission is here, you will prefer this one. So here it's quite a messy plot, but you see there is the emission of different scintillator and the quantum efficiency curve of different type of photodetector. So silicon photodetector, so there is 3 types. So photodiode. So this is a good, in fact, in L3 experiment where there was a BGO crystal used. The BGO has enough light that you don't need necessarily the gain. So we were using simple photodiode. In CMS for electromagnetic calorimeter, we use avalanche photodiode. So in this case, we have a zone of amplification will allow you to have some gain. So typically between 50 and 500, the gain is between 50 and 500. And the new generation was developed a long time ago, but since I think now perhaps 10 years or something like this, are really something going on application is that the silicon multiplier. So in fact, it's avalanche photodiode, but we use in the Geiger mode. And here you have really, you count the photon. So what you do is you have a very small avalanche photodiode, so SPAD, that you put together. So this is a SCPM. And if you zoom, you will see that you have plenty of small SPAD. And all SPAD has in fact quenching. So you do photo counting. So if you have one photon, you will have 1 SPAD signal, 2 SPAD signal, 3 SPAD signal. So, and what you do, most of the time you use in analog mode. So you put together, so all the SPAD in the same connection as you see here. And here again, you can have different photo detection efficiency depending on the type of photo detector. So you will select 1/1 depending on your emission spectra. So I don't know, I have still, so I can start on application and then, so.
We have 5 minutes.
Okay, so I will start and I will continue tomorrow. You have seen already this slide. So as I told you, I will focus on that, but I have few examples of other application. So oil drilling, so you know when you want to make some prospection if you have oil in the earth, so you use also some scintillator crystals. And in this case, you need a high density crystal, good energy resolution. You have to be sure also that it supports temperature. And so usually crystals are sodium iodide and VGO are used, but there is some development to try to find a new material. Particularly, it's important that you have a low dependence in temperature, because if you are in a hot environment and you lose light because the light is depending on the temperature, it will not be good. For safety aspects, so you have also you use some crystals. So here you want to have a very high energy resolution. Some calorimetry for space. So, for example, this is a picture of a thermic gamma ray telescope. So they were using a crystal calorimeter with a cesium iodide scintillator. Search for dark matter. So in this case, what is really important is the purity, because you want really you want to detect very rare events. So you want to be sure that you have low background and you have no emission. And this you work at a very low temperature. So these are pictures of this crest detector. So you see the very nice mechanic and big crystals. And this is an example of xenon. So here, in fact, they use the two properties of a xenon. So both the fact that you can measure the ionization and the emission. And this is a new experiment we are proposed, NXO, where they want to use 200 kilo of xenon liquid. And for that, in fact, they are developing also, they need to develop photodetectors who are sensitive to deep UV and to detect 175 nanometer. And they have some collaboration to develop dedicated SCPM for these wavelengths. This is quite important, because also for, you will see later or tomorrow that for some Cherenkov light, we want also to have deep UV emission. So, I mean, do we have still time, or I can stop here and I will continue?
Thanks, Etinnette. There is a question.
Thanks. So maybe you said it, but what's the main reason for the radiation damage in the scintillator material? And is there a difference in between organic and anorganic?
Why we have
What's the main cause? Like, for example, is it neutrons damaging the structure of the scintillator?
Yeah, it's the structure, et puis the material itself. Generally, the plastic is less radiation hard than the crystals, and there is I think it's one of the open field of research to really understand the radiation damage in the plastic. But I think that these have been less studied than in for the crystals. But I think the crystallographic shape of the crystal, it's help to have a more radiation level materials, in fact, than in the plastic.
Thanks.
Thank you for the lecture. Are there any difference between in the scintillation process produced by charged and neutral particles? And if there are any, how does it affect the luminosity and the wavelength of the scintillation light?
I'm not sure. Can you repeat?
Yeah. I have two questions.
Yes.
Are there any difference in scintillation process produced by charged and neutral particles?
For charged and neutral particles?
Yeah.
Alors, in the Well, charge, yes, because there is the different interaction with the material, and why with photon you create the electromagnetic shower. Why charge particle, if it's hadron, you will have electromagnetic and hadronic shower. So it will be different, and also, so yes, there is some difference in the, but at the end you create light. But
what are the difference in luminosity in the scintillation light produced by
the density?
Luminosity of the scintillation light.
Yes, so some material are very, this is it's intrinsic to the crystal. And sometimes, for example, in PVO, you have low light because we have what we call quenching. So in fact, PVO is has low light field because most of the light is quenched by defect. Or so yeah, you can really, as I show you, you can really have a big variation in the number of photons produced by the crystals. So this depends on, you have seen the yes, so this a part of is here. So if you have a lower transfer efficiency between the electron pair and the luminescence center, and sometimes you can also have some trap, so are non-radiative. So sometimes you have also effect of collective excitation that reduce your light yield. So, and also quenching by temperature. So there is many reasons to.
When we use the silicon detectors, we could have the noise due to the thermal excitation. What could be the noise in the scintillator detectors? What could be the reasons of the noise?
We don't really speak about noise for purely the scintillator. The noise comes more from the photodetector or from electronic. But no, we never use the term of noise for just the material itself. But of course, if you have low light yield and the noise of your photodetector is important, it will have a consequence on your detector itself. So, for example, in silicon PM, there is the dark current, and for example, this dark current will increase with the radiation level, and this has an will change, can have an impact in APD or if you lose gain, you will have less light, and this has a direct importance in your energy resolution. But it's not the crystal, it's not the material itself, it's the full system where you have effect of noise. But if you have low number of photons, and your effect of noise will be higher than if you have a large number of photons. So
on the slide where you showed the list of inorganic scintillators, there was barium fluoride slow and fast.
Yeah, this I will speak quite tomorrow. So because in fact in barium fluoride you have two types of emission. So you have what we call cross-luminescence. Merci. Cross-luminescence are very fast because contrary, it's not the emission is not between at the level of between valence and conduction bands, but between core band and cross-luminescence. So there is a lot of electron and all, and then this is very fast. But you have also what we call the self-trap exciton, who are at the level of the conduction band and the emission band, who are slow. And this, you will see that we have there is a lot of development to try to remove the slow component for fast timing. But you know, here it's when you put that is the main emission. But for example, for PVO, at the beginning, because 200 photons, even in high energy, it's not too much. So we wanted to increase. So for example, we made some tests to to dope with molybdenum, and we were able to increase the light yield of a factor 5, 6. But unfortunately, by increasing the light yield, the scintillation became slower. And as for LHE, we wanted to have a very fast scintillator. We say, okay, we give up because it's not the good direction. So sometimes you have also defect. And due to that, you will have some of the electrons who normally could be used for the scintillation who are trapped. And then after some time or with temperature, they can be untrapped. And it's what we call phosphorescence because there is a delay emission of that. So,
So the last question. Okay. I think that's all. Thank you. Okay, that's all.